Good morning, everyone. I hope you guys went through the lecture from yesterday as well. Let me start with any questions that you guys may have. Question that Shivam has asked is there any relationship between gyromagnetic ratio and atomic mass? Did you try plotting a correlation between the atomic mass and gyromagnetic ratio? Did you try this? That's a good question. So you could generate a table where you have x-axis as atomic mass and the y-axis is gyromagnetic ratio. What is happening as the atomic mass increases? What do you think is happening? Gamma decreases. So your observation is that atomic mass increases, gamma decreases. Is that true? How many of you agree with this? You take proton, you take carbon, it's about 4 times lesser. You take nitrogen, it's about 10 times lesser. So his point is that as you keep increasing atomic mass, gyromagnetic ratio goes down.
One person agrees.
One person agrees. I see. Anybody who disagrees?
One disagree.
One disagree. May I know why you disagreed, if that's okay?
Because in case of fluorine,
very good.
The gyromagnetic ratio is same as that of hydrogen.
Not same. It's lesser than hydrogen. Yeah, about 95% of hydrogen. So that's where your hypothesis fails, right? If you similarly take an example of phosphorus, you increased it, but it's still higher than carbon. Okay, so this is an intrinsic aspect of how the nucleons are packed, and there are multiple other factors that go into it. Okay, it's just not a direct correlation between as you increase atomic mass, gamma reduces. Any other questions? Okay, if there are no further questions, let me go ahead with the lecture. So what did we do in the last class is that we first tried to understand something called nuclear spin quantum number. We said that if this is a non-zero entity, we also came up with some very simple rules to understand how to predict something will be zero or non-zero. Anything that's non-zero will be NMR active, and generally if anything is spin half, it's useful towards studying for some features, which we'll see, right? So now we said that, okay, this nuclear spin quantum number has a given number of states. Let's take I equal to half. It has 2 states, but they are degenerate in the absence of a magnetic field. The lecture I kept on going between magnetic field and electric field. Electric field will not have much of an influence on NMR, but it will have influence on NQR. That's why I said both. But for NMR, magnetic fields is all it matters, right? So now when you have something like this, when you suspend it in a B naught, what we were able to see is that there is going to be a certain energy gap that gets associated. And if I remember correctly, it was like gamma H cross B naught is the overall energy difference between 2 states of spin half systems, where B naught is the strength of the magnetic field, H cross is the unit of the quantization, and gamma is the gyromagnetic ratio of the spin that you're trying to interrogate. What is the next step that we took? I think the next step that we took was to understand how do nuclear magnets orient with respect to B naught. Correct? This was the next question we asked. We took an isolated spin half system. We asked, how do they orient? This is where we left in last class. We also learned that for a spin half system with gyromagnetic ratio greater than 0, alpha will be the ground state, which is a plus half spin state, and beta will be the higher state, which is the minus half spin state. And we said we were also able to calculate that if the magnetic field is applied along B naught, the spin starts to precess about, or at least it's oriented with respect to B naught at 54.7. Correct? The same case for beta as well. Correct? The orientations of the nuclear magnet are not exactly parallel or not anti-parallel. They are close to parallel and anti-parallel. So please be aware, some textbooks would end up calling this as the parallel state, this the anti-parallel state. Although it is kind of easy for classical people to understand that that's not entirely correct. They're not entirely parallel or entirely anti-parallel. But remember, I'm talking about a single isolated spin half. It can either be in alpha state or be in beta state in a given instant. Once we go into the details of the quantum mechanics, we'll be able to understand it probably changes across these states as a function of time. That we will see as we go forward. Okay. So far, I hope you guys are able to understand how when you have a non-zero spin quantum number, especially spin half, there are discretized energy levels that are separated by a certain energy unit, right? And each of the state ends up orienting itself at an angle with respect to the applied B naught magnetic field.
So the angle never changes. Even if we increase the magnetic field.
The angle will not change when you change the magnetic field. That's right. We will look at what will change when you change the magnetic field right now, right? Something else will change, but the angle of the spin state with respect to the externally applied magnetic field will not change. And just to make a few of you guys happy, why do we choose B naught along Z axis? Goes back to a little bit of quantum mechanics. If you guys might remember, we are talking about angular momentum. The moment you go to spin, we are talking about the angular momentum operator. Of course, in quantum mechanics, we would have learned it as L. For people who might not know, please check the rigid rotor model. That's where this operator gets defined. And the angular momentum operator is defined as a cross product of the spatial position to the momentum in 3 dimensions, right? R cross P. And in Cartesian coordinate, you'll be able to write it easily. But remember, the solution for the rigid rotor model came up when you converted X, Y, Z, that is a Cartesian coordinate system, to spherical polar coordinates. So now, the reason why we end up choosing this is that go take a look at the LZ representation in the spherical polar coordinates. It will be something of this sort. That's the most easiest representation, right? If you take a look at the LX and the LZ, LY operators, they're going to be far much more complicated. So the mere fact that you have a very simple representation to look at, we'd rather take the whichever direction we apply the magnetic field to be along Z, so that our math becomes easy. And also remember, from quantum, we have already established some extremely important commutators. Why do we care about commutators? If something commutes with one another, then you can measure each of them simultaneously without any loss of accuracy. That's the, I mean, it goes with the Heisenberg's uncertainty. The mere fact that when you have a commutator that is going to be non-zero indicates that you cannot measure those two variables simultaneously and accurately, right? You can measure them, but they're going to be inaccurate. Only one will be accurate, the other will be definitely inaccurate. This is Heisenberg's uncertainty. So now that we have established our definitions and also some of the very important commutators to know where the total angular momentum commutes with the Z component. Remember, the total angular momentum commutes with LX and LY as well, independently. But we tend to take a frame of reference where this is fixed, so life is easy. If you ask what is L square, comma LX, that will also be equal to 0. There are no surprises there. They will also commute. But given the fact that the moment you set the commutator 0 with respect to Z, then there's an uncertainty expected from X and Y components. We'll see what these mean as we go forward. So instead of using L, we'll start using I, and we will literally keep all the concepts that you have learned from quantum mechanics and angular momentum for this course as well. Does that make sense? So what did I try to tell you? Why do we always try to say align B naught along Z? Is because it has a really simple representation and we have some outcome from quantum mechanics which we can directly borrow. So let's ask the next most pressing question. So you have the alpha state and you have the beta state where alpha is the lower in energy. So the question we have here, what is the energy of this alpha state, right? We said energy is going to be given by minus mu dot B. And then we reduced it to minus gamma B naught MH cross for a given state M, right? So using this definition, energy of E alpha is going to be minus gamma B naught H cross by 2. And energy of beta is going to be gamma B naught H cross by 2. Therefore, the delta E that we are trying to talk about is E beta minus E alpha in this case will be gamma H cross B naught, right? Now that we know the energies of these two states, the next question that comes up is what is P alpha, what is P beta? Why is this important? Spectroscopy works from the fact that if the delta P, which is like mod of P beta minus P alpha, is greater, the more the sensitivity. Population difference is higher, then more sensitive. right? More the population difference, more the sensitivity. So the major aspect that we need to understand, what is the population difference? Let me try to derive it as in the textbook for a general case of spin, not just for spin half. So let's say we take a spin system I, and it has states that goes from minus m to plus m in integer steps of 1. So therefore, population in a given state m with respect to the total population is going to be given by the Boltzmann's distribution, where there's going to be e power minus em by kbt, the whole divided by summation over all states for e power minus em by kbt. And this is what is called the Q factor that comes in the Boltzmann's equation. It's more like a normalization factor. What did we say em to be equal to? We said it's gamma h cross b naught m. Correct? So therefore, minus em by kbt will translate itself to be gamma h cross b naught m by kbt. I want you guys to solve this as we are in the class. What is the value of gamma for a proton? Do you guys remember? Some of these constants are good to remember. Please try to remember wherever you can. And then let's assume B naught is, let's say 9.4 Tesla. And then let's say we take a temperature of 298 Kelvin. What I want you guys to do is to calculate what is the ratio of gamma h cross B naught m. Forget m right now. Gamma h cross B naught. M also you can put. M is half, right? Just put a half. It's plus or minus half. So you can put a plus or minus sign later on. So m equal to half. Calculate the ratio of gamma h cross B naught m by kbt.
Around 10 to the power 2 into 10 to the power minus 4.
That sounds about right. So what you guys are able to see is that the value of the gamma h cross B naught m by kbt for spin half system at 298 Kelvin and 9.4 Tesla comes up to something like 10 power minus 4, right? You guys might remember e power x expansion, Taylor series expansion is given by 1 plus x square plus x power 4 and so on until infinity, right? And what you're able to see is that if x is small, then x power n is smaller. So therefore, what's going to happen if you are having 10 power minus 4 in power of x, you can be rest assured that all this ends up going to 0, correct? So therefore, we can estimate e power x is approximately equal to 1 plus x for small x. Do you agree that x is small here? 10 power minus 4. It's really small, right? So therefore, what is going to end up happening? The population of state M is going to be given by 1 plus x, which is going to be gamma h cross B naught m by kbt. The whole divided by summation over m goes from minus I to plus I, e power plus gamma h cross B naught m by kbt. As much as we applied the approximation to the numerator, you can still apply that to the denominator as well. The reason why I didn't write this is that I want you guys to think. Realize that it is also going to get expanded with m being one of the index. So let's write it. So this is going to be 1 plus gamma h cross B naught m by kbt. And what are the indices of m? It goes from minus I to plus I, correct? So for every value of I, there's a minus I that's associated with it. So therefore, you guys realize that when you do the summation, this entity will go to 0. Of course, the 1 will keep on staying for every value of I. And how many times does it stay? It stays for every value of I and goes from minus I to plus I. So if you think about it, this will end up being 2I plus 1. So therefore, Pm over P is going to be given by 1 over 2I plus 1 times 1 plus gamma h cross B naught m by kbt. And we will say that this can be approximated as 2 into 10 to the power of minus 4, correct? So what is going to happen here? And we are talking about spin of half. So therefore, this will end up going as 1 over 2. So you're talking about 1 over 2. P of half over P is going to be 1 plus 0.0002. Correct? So what is that going to be? Equal to divided by 2 will be 0.5001. Correct? And therefore P minus half over P is going to be equal to 0.4999. You guys see that? So the population difference for spin half system turns out to be P alpha, higher populated state minus the lower populated state. So this is going to be 50.01% minus 49.99%, which is 0.02%. You guys see how low a population that difference that is? Not a huge difference that comes up, but luckily chemistry works in our favor. If you take 1 mole of a substance, you have about 10 power 23 particles or molecules in it. So therefore, it's still a good number. For 1,000, it's about 2, but if you go for a mole, then the difference starts to be sizable. There's an exercise that I want you guys to do. The homework is going to be, in this example, we assumed the value of gamma to be for proton, and we assumed the value for B naught, which is the magnetic field, and of course, a temperature. What I want you guys to do as a first exercise, change the temperature to 100 Kelvin and tell me what is the population difference for the same B naught and gamma H. All I'm asking is reduce the temperature from 298 Kelvin to 100 Kelvin and tell me whether there is a discernible difference that comes up. Okay. The next aspect of this that I want you guys to work out is to keep the temperature at 298 Kelvin. Compare for proton, carbon, nitrogen, and deuterium as well. So try to check what will be the delta P given the B naught of 9.4 Tesla at 298 Kelvin. Yeah, this is one other exercise that you can do. The last exercise that I want you to do is keep everything constant, T equal to 298, and it's for proton, but change the B naught from 9.4 Tesla to something like 18.8 Tesla and tell me what is the delta P. I'll give you the outcome already, but think about it after you get the numbers. What you'll be able to realize is that reducing temperature to 100 Kelvin does not help in increasing the population as much. Okay. And more importantly, when you're checking across gyromagnetic ratio for a given value of B naught, as the gyromagnetic ratio reduces, the population difference reduces further. Right? No surprises. If you're getting the energy levels close and close to each other, the populations are going to become more equal. Only when you're going to take them farther and farther, that's going to help. And of course, the only way to make the energy levels go farther and farther without the handle of gyromagnetic ratio is B naught. So therefore, if you double the magnetic field strength, check whether the population difference doubles or not, or it increases more than whatever it has to increase. Okay, so just to get an idea of what's going on. So what have we told thus far, yesterday and today? Non-zero magnetic spin quantum number, when suspended in an external magnetic field, results in a discretized set of energy levels, each state having a certain orientation with the external field and having a certain population difference. And what does the population difference depend upon? Ensemble of spins. What do we mean by this? We are never going to have one isolated spin half to worry about. Whenever you make a sample, so getting a sample at 10 power minus 23 molar is very difficult. You can never make a single molecule unless you do a few other things to it. Right? You'll always have a group of molecules, right? So now we want to understand how do these spin states manifest themselves when you have a larger number of samples that exist. Okay, so you have this right now. Now what's going to end up happening? You guys realize that there is a certain population associated with alpha state and beta state, which are non-zero. The moment you say you have a certain population, you have a number of them. I'll tell you why I'm fanning them out. In theory, you could have drawn many on this itself, but that does not happen. We'll talk about that in a minute. So you have a bunch of spins that exist about that orientation. All of them will be at 54.73 degrees with respect to Z or minus Z, but they're going to have a number of them. The number depends upon what is P alpha and what is P beta, right? For instance, there will be 5001 here, That'll be 4,999 here. Now the question is, why do they fan out into a cone? Yet again, if you recollect yourself, while you have the ability to clearly distinguish what is a Z projection, you have no way of precisely saying the XY projections. Therefore, every possible position across X and Y is feasible. Okay. Therefore, there is a randomness that's associated with the transverse XY plane with respect to the B naught that is applied. So from here on, whenever I mean a transverse plane, I mean the X and Y axis or the XY plane. And when I mean longitudinal, I mean anything with respect to the Z axis. Anything that's a transverse plane indicates that it's along XY plane. Anything that's a longitudinal is along Z. Yeah. Now, remember one thing, the number of vectors along alpha is going to be more than the number of vectors along beta. So let's take these two axes, and just for the sake of simplicity, let's assume one of the alpha spin state along the ZY plane. It doesn't have to be, let's just take one for instance, right? At least that'd be one, right? And what you could do to this vector, remember there is an angle theta that's associated with it. And you can always resolve this to the mutually perpendicular components. Correct? There's going to be a component of this size. There's going to be a component of this size. True? But fortunately or unfortunately, what is going to happen? You have every possible orientation along the transverse plane. Right? So if you take each one of the spin and resolve them into its mutually orthogonal components, you're going to keep on adding up along the Z, but you're going to have everything pointing along X and Y for the transverse component. True? So what is going to happen? Let me try to draw some X and Y projections. If you're looking at Z axis this way, your Z axis is pointing up towards you. You're going to have every possible orientation that is resolved, resulting in net zero along the transverse plane. Everybody in page? What did I say? You take a vector and resolve it into two mutually orthogonal components. The component along Z for each of the alpha spin state will be adding up with each other. On the contrary, since there is no transverse proper population that exists, the transverse component will cancel with each other. Correct? So the transverse component literally goes to zero after vector addition, or zero or close to zero, right? So small that we can't observe. But on the other hand, the longitudinal component will keep on adding up with each other for each of the spins that are being present in the alpha state. True? We can draw a similar picture for beta state as well, where all the transverse components will cancel each other, but the longitudinal component will add up, but will be along the minus Z axis. This will result in a scenario where all the alphas will bunch up and add up together. All the betas will add up, and we can call it a magnetization because we are talking about the net equivalent that comes as summation over all the spins. But merely because of the fact that P alpha is greater than P beta, it implies that the magnetization of alpha will be greater than magnetization of beta. And you have opposite vectors that are being present, and this will result in a net magnetization, which we will call as M naught, which will also point along the B naught axis. This is called the bulk magnetization. So therefore, we have a net magnetization that is a vector sum of M alpha and M beta. Since they are pointing in opposite directions, they will destructively interfere where the difference comes up is proportional to the differences in populations that exist. This is a very, very important cornerstone of us understanding how NMR can be defined classically. The next 3 lectures that I'll be dealing with will only be dealing on how do we manipulate this magnetization to extract the parameters of our interest. Most importantly, the chemical shift. You remember the first lecture where we said it's important to understand what's a chemical shift because that helps us understand what kind of chemical moiety it is, right? All that information content, not just chemical shift, there's something called scalar coupling, there's something called integrals, there's something called dipolar coupling. A lot of things are present within this magnetization. And if I'm able to measure this magnetization, you can extract all this information. The question that is being raised by one of the student here is that why would M alpha and M beta be different and why would it go with populations? This is question. The answer to this is that, do you realize that for each spin that exists, they can be resolved into the mutually orthogonal components, right? And if you have P alpha number in alpha, right, you're going to have P alpha number that's going to be here and here, but in the transverse, it's going to get subtracted. You have no doubts on that, correct? But the longitudinal is going to add up depending upon how many vectors were there in alpha. And how many vectors in alpha is driven by P alpha. How many vectors are there in beta gets driven by P beta. Do we agree that P alpha, P beta are different where P alpha is greater than P beta? Therefore, P alpha minus P beta is greater than 0. So therefore, the vector addition would result in a non-zero magnetization that points along the z-axis. The next class is going to be very heavy on understanding how does the magnetization evolve as a function of time. And that will help us learn how to extract that information out of M0. Although I did draw each of the alpha state as a vector, remember, a given magnet in a magnetic field will experience something called a torque. Okay, so there's a magnetic field, and so there's a magnetization, a magnetic field, and the magnet will therefore work with it. So the torque will make each of the state presses about it. So although I did draw them as stationary, in reality, each of the vector is also precessing. What is a motion? Precession. Each of the quantum vector will keep precessing about the B naught. Same would be for the beta. Beta will also be precessing. Now the direction of precession, whether it's clockwise or counterclockwise, will be determined by the gamma. If the gamma is positive, we can assume that it goes clockwise, then gamma is negative, then it goes counterclockwise. Okay, so each of the spin state is precessing. But interestingly, the ensemble average of all this results in a bulk magnetization that's along B naught. So therefore, this bulk magnetization will not precess. Precession is, let me write a little bit of torque. Torque will be given by something like M cross B. You can imagine the magnetization is M and the B naught that you're applying is the B, right? The field is along the Z axis and the magnetization is along the Z axis, again, the bulk magnetization. What is cross product of K times K? 0. So therefore, no. So the bulk magnetization is stationary along the B naught that you've applied. So this is where a lot of confusion would happen in NMR. We will call something a magnetization. We'll call something a magnetic field. Magnetization gets developed from the sample that you have put in the spectrometer. Magnetic field is something that you are applying. Okay. Lot of upcoming next 3 lectures, I'll be using both these words. If I'm using them very fast and you're losing what am I saying where, please ask me to repeat, let me repeat. Okay. Whenever, therefore, going by this equation, you realize that if the magnetization is not along Z or even tilted away from Z, then you will have precession that happens for magnetization. Yeah. So this is a common feature of NMR. You're going to see precession in different forms. But let's go to that in the next class. But I want to make sure you guys have understood that when you end up putting a sample inside an NMR magnet that has a non-zero nuclear spin, you're going to have a bulk magnetization that is oriented along the direction of the external magnetic field you applied. So as much as I did say that delta E is going to be gamma H cross B naught M, not M. M won't be there. We are talking about spin half systems. So let's talk about delta E of spin half. It's going to be gamma H cross B naught, which is also going to be equal to the H cross omega naught, right? So therefore, the omega naught is going to be given by gamma B naught. This is the Larmor precession frequency. For a given constant B naught, depending upon the nuclei, this precession frequency is going to be different. And the super cool aspect of NMR is that the energy difference between the alpha and beta states matches with the frequency of precession. So what are we trying to say? The alpha beta states that presses about B naught presses at a frequency that's similar to the frequency difference between the two energy states. This aspect of NMR allows it to be visualized in a classical manner, and you in fact don't need to invoke any quantum mechanical principles to understand NMR. Now, try to go back and calculate different Larmor precision frequencies for different spins, but let's take proton. And when we said B naught of 9.4 Tesla, can you guys please calculate what will be the omega naught? Please be careful about units. 2.51 into 9. 9? Second inverse. You would have to divide it by 2 pi.
3.99.
Yeah. So divided by 2 pi, right? So you still have to divide it by 2 pi to get radians per second. So basically a 9.4 Tesla magnet results in a 400 megahertz proton Larmor precession frequency. Okay. Go back and try to do it for carbon 13. It'll be approximately 1/4, which will be 100 megahertz. Right? And try to do it for 59, that'll be close to 40 megahertz. Of course, I'm giving approximate numbers, but you guys should be able to precisely calculate it depending upon the gyromagnetic ratio. Right? This is independent of temperature. Once you set B naught, the Larmor precession frequency is set as a constant, right? The SI units of magnetic field is Tesla. But if you speak with NMR spectroscopists, when we talk about a magnet, we'll say, oh, it's a 400 megahertz magnet. You should also think about what is 11.4 Tesla. I think what is 16.6 Tesla, maybe. And then what is, and also convert the other thing. 1 gigahertz has to be how many Tesla magnet?
This definition changes if you change proton.
That's exactly correct. So generally, we only speak about magnetic field strength with respect to proton. Proton is one of the most abundant nucleus, the most probed nucleus, has a spin half. So therefore, we end up standardizing everything against the proton. The moment you know proton, if you know the ratio of gyromagnetic ratios, you can predict the rest. Isn't it? So that's the whole idea here. So I hope I have driven a few important aspects that we need to understand about NMR, where when you have a spin that has a non-zero, when you have a nuclei that has a non-zero nuclear spin quantum number, it has discretized energy levels, and when suspended in an external magnetic field, has energy difference that nicely correlates with the motion of precession and gives a bulk magnetization. If possible, I request you guys to read the next part of the Kamana book, which deals with block equations, which talks about the cross product of M cross B, which I alluded to briefly today. Read and come. Don't worry if you don't understand, because it's a concept that's not very easy to understand the first time. You read and come, when I explain, maybe things will get a little more easier. Thank you very much.